Hello, we will be working on problem 8-3 from Integrated Math 3 from CPM. So we are going to be graphing polynomials. These are a general sketch. They don't have to be incredibly accurate. I do want very accurate x-intercepts because from factored form, which most of the polynomials given to us in the very beginning parts of chapter 8 will all be in factored form. So we should be able to clearly identify the x-intercepts and some general behaviors based on any time you see a repeated factor, as well as start gaining an understanding for, depending on which family of functions a polynomial belongs to, it starts and ends in a similar fashion. And so we're going to start thinking about that, those patterns as we start generating these polynomial graphs. So the first polynomial graph is P1 of x equals the quantity x minus 2 times the quantity x plus 5 squared. So I see a repeated linear factor here, so I was going to identify that there is a repeated linear factor. And what you'll begin to understand is that anytime this happens, similarly, if we were just looking at a quadratic function, this means that the graph will bounce off of the x-axis here. It bounces off the x-axis. So that's one of the things I noticed looking at this equation. Another thing that I noticed is that there is another linear factor, the x minus 2. And so that also introduces another x-intercept. And so the concept I'm using to figure out the x-intercepts are again when the output is equal to 0. So when does 0 equal this polynomial expression? And so thinking about that, the values that actually make that polynomial equal to 0 are the values of 2 and the negative 5. And so again, I'm just going to write here that we've got an x equals 2 and also an x equals negative 5. Those are our x-intercepts using the concept of zero product property. And those help me find values on my graph to quickly generate a very nice looking sketch. Again, we've got the value of 2, and then we've got the value of negative 5, which is over here. And remember again that this is a cubic graph, and it's going to bounce here. So you're supposed to use technology to kind of help you to understand more about what these look like. But before I go ahead and use the technology, I wanted to talk about how did I just determine it was cubic? Well, it's because if I think about multiplying this entire equation out, the x plus 5 squared would be x squared plus 10x plus 25, being a quadratic. And if I multiplied it by another linear factor, the x minus 2, my highest ordered term would be x cubed. Therefore, this is a cubic function family. So the function family that this belongs to is cubic. And again, the reason for it is because if we think about multiplying it out, we would have an x cubed term as our term with the highest exponent. And that also, when they ask you what's the degree of the polynomial, the degree of the polynomial is dictated by that exponent's value. And so the degree of the polynomial is 3. Now, another thing is I can actually therefore call this a third degree polynomial. Polynomials are multiple polynomial. They are going to be like functions that have powers that are only whole numbers. For example, x to the first, x squared, x cubed, x to the fourth. They're not going to be powers that are negative 1 because that's not a whole number. And they also won't be fractional, like a square root. It'd be a fractional power. So please look at the notes for the definition of a polynomial. So let's talk about one other thing that I could figure out before I use the utility of the calculator to figure out what this graph looks like. We can find the y-intercept. So how do you find the y-intercept? So as a reminder, the y-intercept is when your x value equals 0. So you could substitute that into my equation to figure out, well, what is the output when you input a 0? So what's 0 take away 2 times 0 plus 5 squared? Being very careful with order of operations, you're going to add the 0 plus the 5 first to get 5, then square that. And so that would become 25 before we multiply it by the negative 2. And negative 2 times 25 is negative 50. So our y-intercept is at 0, comma, negative 50. And now I can use this graph that I've already generated and scaled my axes to show that y-intercept there is at 0, comma, negative 50. And to use a graphing calculator to kind of help me understand, I mean, I remember that cubics generally go like that, right? They come around something like that. But if you use a graphing calculator, and here in your y equals, when you turn this on, I've already put in my functions that I'll be exploring today. And so if I look at the first graph of this, I can see that, you know, it looks kind of like a cubic, but a little bit different. But it has that same general shape. And again, notice that it starts at the bottom here and it comes up and then it finishes up high. And so I'm going to match that sketch. And notice right here that it also bounces off of the x-axis at the negative 5, which is one of the roots. And so again, I'm going to sketch this curve. So it starts on the bottom and then it comes here, bounces off that first x-intercept, and then it comes back down here and it starts coming up again, and then it passes through that other x-intercept before continuing on. So one of the things to notice is that this point right here, the y-intercept is not always the lowest point, say, on this curve here. And again, I'm going to show you what it looks like over here. There are ways in calculus that we will learn, well, how do you figure out this value so that I could have a very accurate sketch? And in this case, we're just doing more or less a rough sketch with clearly showing x-intercepts. Anytime we have bounces or passing through or flattening, which we'll talk about later. But since I've got my graphing calculator out, and some of you might remember when we had hit second calc, we're able to find values for different x values that we can put in. We can confirm what those x-intercepts are. We can also find minimum values, maximum values, and intersection points. So just in the extra 30 seconds that I'll take here, I was going to find what is that minimum value right there. If I hit enter, it asks for the right bound. It looks like the left bound is over here, and I take a guess. This shows me right here, if I zoom in here, that even though the x-intercept's at negative 50, there's actually a point that's lower than that. That's actually at negative about 1/3, comma, negative 50. Now, I do not expect you ever to graph these additional minimum and maximums, but know that when you get into calculus, you'll learn about derivatives and how we can find these values very quickly and accurately. Please watch the remaining couple videos that I will post if you're curious about taking a look at the other polynomials.